Okay, guys, I'll just give a quick update as an announcement, and then we can jump in the lecture. So the update is that I've set the lectures for the last 3 classes. I can't make this bigger for some reason. Huh. I actually can't make this bigger, sorry. So next week is Frank Wolf, which is, I think, a very cool method, very relevant for today's landscape, just like ADMM and coordinate descent. Then it's Thanksgiving. Then these 3 lectures, I haven't updated them on the website, but I've more or less set them now. This one is going to be, this Monday we're going to talk about SGD again. And currently it's called fast stochastic methods. We'll do a mixture, probably, of talking about variance reduction and momentum, that lecture, for SGD. This one we're going to talk about mirror descent, which is it's a nice thing to learn. It's like a twist on gradient descent, essentially, that can be very useful for some problems. It's listed as online optimization, but probably we'll just talk about mirror descent that day, which could lead into online optimization, but it's not clear how much we'll cover. And for this one, we're going to have a guest lecturer. And this last one, I'm going to do one of 2 things. So I assume a lot of people have gone at NIPS this week. This last lecture, I'm going to either talk about non-convex problems that are benign, which means that we can solve them exactly. So there's just a bunch of interesting problems I'll list. Or I'll talk about integer programming. So I may do a poll for this last one, but the plan is either one of those 2. And as I said, I set these last ones before that. Okay. And the homework, by the way, that's due, homework 5, is not on any of that. In fact, it's not even on ADMM, so it's something that we released early, and I wrote it with the intention that you could solve it like right away. It just essentially covers some coordinate descent, and mostly it's just generic problems that involve convexity and duality, and all of this is supposed to be interesting and fast-paced, and you're not going to be having to know it for the homework. Or, I mean, yeah. Yeah, that's right. Yeah, so I was about to say that. The little test will be comprehensive, so it'll cover all of this stuff. It will not cover this. So whatever I talk about this last December 3rd is going to be like truly optional in terms of it. Just trying to expose you to interesting things that are non-convex. But yeah, the little test will, at the same level as the previous little test, test a very cursory understanding of the other stuff. So for that reason, you should still pay attention to ADMM and Frank Wolf and mirror descent, etc. Plus, you should pay attention because they're interesting. Okay, so today is ADMM. Very kind of natural follow-up or transition from last time, because last time we did talk about ADMM. We just talked about dual ascent as the primary driver. So I'll just remind you of what we learned last time. We have a problem of this form. Minimize some closed convex functions subject to equality constraints. F here is, it's closed and convex kind of in the most generic case, but I wrote down strictly convex here so that the conjugate is differentiable of F, which we learned last time. And we write the Lagrangian that we know and love like this: f of x plus u transpose ax minus b, u being the dual variable associated with that constraint. And what we learned is that we could get subgradients, or in the case of a strictly convex primal f, actually gradients of the dual criterion in the following way. We solve this minimization problem. So given a u, we minimize f of x plus u transpose ax minus b. We take that x and we plug that into ax minus b, and that gives us a gradient of the dual criterion. Okay, so this construction came from the relationship between subgradients of a function and subgradients of its conjugate. And so this is actually a bona fide gradient ascent on the dual, and this is just the way this is just a step we use to compute the gradient. The good about this method is that it can decompose when f does. So if f is decomposable across blocks of coordinates, then each of these gradient the gradient computation decomposes as well across those blocks, which makes the dual computations decomposable, and hence, if you have like a nice parallel computing setup, very efficient. That's the good. The bad is that we require strong conditions on F in order to ensure primal convergence. So to ensure dual convergence, we knew that was the case. I walked through that with you last time. That's just due to the fact that you can relate curvature information about F to curvature information about its conjugate. So this was gradient ascent if we chose the step sizes properly and we assumed things about F that implied things about the dual criterion, then we're just applying gradient ascent. And so we know that we get convergence of the dual criterion. If you want convergence in the primal, it turns out that that requires more stringent assumptions. And in practice, these assumptions aren't always satisfied by kind of common problems we want to solve, so this doesn't have the greatest convergence properties, even though it decomposes. So we talked about modifying the problem so as to strongly convexify the criterion and get better conversions. And one way to do that was to add a term to the criterion that looked like this. So rho over 2, the norm of ax minus b squared, with the idea that at any feasible point, this term is 0. So it won't change the problem. That does make the criterion strongly convex. At least if A is full column rank, then this is a quadratic, it's strongly convex. It makes the whole criterion strongly convex. And it actually leads to a different algorithm. So if we look at the same dual ascent algorithm applied to this primal problem, then this changes. So the computation of the gradient changes. It's actually a different algorithm. And the Lagrangian becomes augmented by this quadratic term, hence the name. So this had the advantage of actually improving conversions, because we've added the strongly convex term to the primal criterion. It had the disadvantage of ruining decomposability. So once we did this, if F was decomposable, then in this step, the gradient computation, when we go to compute the dual gradient, doesn't decompose across blocks anymore because of this term. Okay, so we arrived at this thing called ADMM, which I'll remind you about now, which tries to combine the best of both methods. And it applies to problems of this form, although in this lecture especially, I'm going to show you how to get problems in this form that aren't obviously in this form to begin with. Okay, so for now, think of this form as being, you have to just trust me that it's a fairly flexible form, and we can actually get a lot of problems to fit this form. So we have a criterion that looks like f of x plus g of z, and we have an equality constraint that looks like ax plus bz equals c. And we form the augmented Lagrangian for this problem, which is exactly this. It's just following the previous slide, but now our variable is xz. And instead of computing the gradient by doing a minimization of the augmented Lagrangian over all of the primal variable, xz, we actually break it up into two steps. So we fix z and u, minimize over x, and then we fix x and u, minimize over z. So we force it to be decomposable across these two blocks, even though, somewhat technically speaking, if we were actually computing the gradient, it would involve a joint minimization over x and z, right? X and z here. That would just be dual gradient ascent. And one important detail, which was also true of coordinate descent, you'll notice that this is actually xk, not xk minus 1. So we have to use the most recent x in the z minimization. And then we just perform gradient ascent. Okay, and for reasons we went through last time, there's actually a very natural choice of step size here. That choice of step size ensures that the stationarity condition for the original primal problem, without this augmentation, with this guy, is satisfied at any x and u iterate. So that was a very natural choice of step size. And then to get the KKT condition satisfied, it suffices to have primal feasibility. So you can imagine somehow we've already satisfied part of the requirements for optimality just by taking the step size, and the algorithm is going to drive the iterates into primal feasibility as it goes on. So this is going to approach 0. Once it does, then we have, by the KKT conditions, a solution. So went through this last time. I'll just very briefly repeat it. I just said this. We get primal feasibility in the limit. Therefore, because of the fact that rho is designed to give us stationarity, or the step size is designed to give us stationarity, we take the step size equal to rho. We get the KKT condition satisfied in the limit, and so we get convergence of criterion values. And we get an even stronger result in the dual, so we get convergence of the iterates themselves. So the dual iterates actually converge to dual solutions. And there's a lot of, so there's older papers that establish this, but then Steve Boyd has a monograph recently, which I think has a fairly approachable proof with, fairly general conditions on the functions for this to happen. And in terms of rate, I mentioned that this is still, there's still actually ongoing work that establishes convergence rates for ADMM, but roughly speaking, you can think of it behaving like a first-order method, so converging like a first-order method. So you get the standard rates under the standard assumptions. And there's some very interesting work. I guess I'll point out this work in particular, which tries to establish the contraction factors for ADMM under the strongly convex case. So remember, first-order methods, they are kind of badly affected by conditioning. So they converge at this linear rate under strong convexity. If you give me strong convexity plus a gradient that's Lipschitz, they converge at this linear rate like log of 1 over epsilon. But the constant multiplying that, or the contraction factor, if I think about it as something to the k, depends on the conditioning quite poorly. And it's very clear when you see what that contraction factor is. And we even saw this manifest itself in the linear systems lecture, that gradient descent converged at like kappa times log 1 over epsilon, where kappa is the conditioning number, right? So gradient descent for quadratic problems is like this, where that's the condition number of the matrix in the quadratic form. And conjugate gradient actually converged like this. And by the way, so does accelerated gradient method. It also has the same dependence on the condition number, kappa. And coordinate descent appears to have this as well, although I don't think that's established in kind of full generality yet. So I guess I'm saying that, everything behaves like a first-order method, but the details matter. In particular, some of how does it depend on conditioning. And this last paper, in case you're interested, it tries to work out the contraction factors, so essentially what goes here, for such a rate for ADMM. And people observe that somehow, like under suitable parameterizations, ADMM might actually be converging better than first-order methods. It's just not really clear at this point. In terms of the, let's say, better than standard gradient descent or proximal gradient by the conditioning. And this paper actually solves for the contraction factors by solving an SDP. So it can compute for you in practice what the contraction factor will be in your problem by solving another optimization problem. And I think it's a very kind of creative analysis because it's very non-obvious what to do for ADMM. So in case you're curious, I just wanted to point out that paper as being interesting. Yeah?
We're assuming ADMM behaves like first-order method. Are we assuming that the cost of computing gradients is the same as the cost of solving this linear optimization problem?
It's a good question. I'm not really talking about like the iteration cost here, but I was associating iteration complexity. So implicitly, yes. Okay, we're going to see for certain problems where you could apply proximal gradient, ADMM will be no more expensive iteration-wise. So like for the lasso, you can apply proximal gradient, you can apply ADMM. They have same costs. They should be converging at the same iteration complexity. In some formulations, ADMM will be much more expensive per iteration than a first-order method. But I would say that's mostly because it's so flexible. So you can solve problems where you wouldn't know the proximal operator to begin with. So yeah, in cases where it's like it's a simple enough problem, it's usually comparable, but then you'll see other applications where it's much more expensive because it's a very flexible framework. Any other questions? Yeah.
Yeah, so since kind of the way we update the arguments at the arguments G are non-symmetric, like are there kind of theoretical differences in terms of, like, are these assumptions on f and g non-symmetric too, and in practice, like, which function should we use to choose to be our f and which
Yeah, that's a good question. So the analysis does not separate them. They have the same assumptions. Essentially, the only assumptions are that you get strong duality in this problem, or the 8mm problem. Okay, that's the only assumptions we need, is that this has to have a strong dual. Once you have that assumption, then the results apply. You are right, though, that in this update, I'm not treating them the same. And in fact, if I updated z first and x second, it would be a different algorithm. So in practice, it would not give me the same iterates. But they're both fine. I mean, what I call x and what I call z is invariant somehow. I mean, I'm allowed to switch x and z notationally. There's nothing stopping me from doing that. And then it leads to a different algorithm. So you are correct about that. Usually, it doesn't really matter somehow. Like after, so many iterations, they'll be converging very similarly. What does matter, okay, is not the order of these updates, but we're going to see at the end of this lecture is the parameterization I use to take a problem from like generic form to 8mm form. So typically, there's not just one way to do that, and that will affect convergence a lot, which I'll show you an example at the end. Any other questions? Okay, and the last thing was scaled form, which this is the way I remember it from now, at least the way I tend to think about 8mm is in scaled form, where we're just changing the dual variable from u to u over rho. So I'm just going to scale the dual variable and write everything in terms of this new variable w. And it just makes the updates simpler to write down. That's the only reason why. Okay, the augmented Lagrangian piece, the Lagrangian plus augmented Lagrangian pieces just become, if I think about the dependence on x and z, well, that's a typo. That should have said f of x plus g of z plus rho over 2 ax plus bz minus c plus w norm squared. So that's supposed to be a z on the slide. It was just an x. That's just a typo. So that's the augmented Lagrangian in scaled form. And then that's my L of rho. And then I just alternatingly minimize this over x, over z, and then do a gradient ascent update for w, which gives me this algorithm. Okay. So here's the rest. What we'll do the rest of today. We'll talk about a bunch of examples and some practicalities, like the important things that I guess you should know before you go and deploy 8mm in practice. Then I'm going to talk about a very useful thing called consensus 8mm, which is going to give you something that looked like dual decomposition in its original form. So you're going to be able to actually take problems and like massively distribute computations more so than what's revealed by this. This just looks like I'm doing, two smaller minimizations one after the other. But you're going to see by using particular parameterizations of problems to take them into 8mm form, we can get like decomposable algorithms. And the generic name for that is consensus 8mm. And then I'm going to talk about at the end special decompositions that I'll just give you an example, but then refer you to some papers which investigate the fact that if you take problems into 8mm form, it somehow matters not only in terms of decomposability. I mean, more broadly, it matters how you parameterize them in terms of the convergence rates you're seeing in practice getting out. And that's not explained by theory currently. It's just an empirical observation. So, okay, I guess this was not quite an example or a practicality, but it's something I wanted to point out. It's the connection to proximal operators. You've already seen proximal operators in a bunch of different settings, proximal gradient being the primary time you've seen them. This is the connection between 8mm and proximal operators. It's through an algorithm called Douglas-Rackford splitting. So if I had this problem that looks like just f of x plus g of x, I can write this as f of x plus g of z subject to x equals z. Now it's in a form that I know I can apply 8mm to. And so what do the 8mm steps look like? Right, this is what I have, by the way. This is my augmented Lagrangian. Rho over 2 x minus z plus w, norm squared. And there's the W piece. This is my augmented Lagrangian in this case. And so the x update, if I minimize this over x, I'm going to say, let's say x plus equals the argmin of f of x plus rho over 2. Let's write this as actually w, or rather z minus w minus x norm squared. Okay, and what is that? That's exactly, so I can, let's say, divide the criterion by rho, divide the whole criterion by rho. Then look what this looks like. This looks like 1/2 the norm of something minus x squared plus 1 over rho times f of x. That's exactly the proximal operator of f evaluated at the point z minus w. It's just, that's by definition. So it's prox of f with a parameter 1 over rho of z minus w. Okay, and for the same reason, this is what the z update looks like. It's the prox of g at the parameter 1 over rho evaluated at the point x plus w. And then I do a dual update. So Douglas-Rackford splitting was an algorithm that was proposed, I think, earlier. I think it was in the 50s, if I'm remembering properly. It's an older algorithm than ADMM. ADMM recreates this method in this special case. And you can think about this as a proximal algorithm where you don't know that f or g, you don't know that either one is smooth. If you knew that one of them is smooth, right, if I have f of x, which is smooth, plus g of x, which is convex, but not smooth, then I would apply proximal gradient, and I would only be using the proximal operator of g, right, if f was convex and smooth. But if I don't know that either of them are smooth, this is the natural thing to do. It's called Douglas-Rackford splitting. I actually alternatingly apply their proxies. Okay, so it's a nice extension of what we learned for proximal gradient, and it's a special case of ADMM. And in fact, maybe an advanced connection that I'll just mention is that, this may not be obvious from first sight, you can actually derive ADMM in full generality from this algorithm. So this is not a special case of ADMM, it's actually equivalent to ADMM. Turns out for any one problem, ADMM on the primal is the same as Douglas-Rackford on the dual. They're the same algorithm in general. So this is actually like another way of seeing it. It's just through, it looks like a specific case with respect to this slide. Okay. In general, yeah, I guess aside from simple cases like this, you're going to see proxies appearing a lot in ADMM steps. And that's going to be in the case if you have a block of variables, if the corresponding linear transformation that multiplies those variables, right, in a formulation like this, is identity, then you're going to see the proximal operator appearing in the update for that variable. Because you'll have a quadratic term that looks like just that one variable, let's say x, minus a bunch of stuff, and you'll have f of x appearing. When you have a non-identity linear map multiplying your variable, then it's not quite the proximal operator. In that case, we know it's like we call that a scaled prox when we talked about proximal Newton. Okay, but there's that relationship that's just important to be aware of. So let's do an example now. Enough kind of talking about these generalities. Let's do an example, and you'll see that the prox comes out of the L1 norm, which is soft thresholding. So let's recall our friend the lasso, which you guys maybe are sick of by now. We have several algorithms for this guy, and ADMM gives us a different algorithm than all of them. And what we do is we take, we replace the beta in the L1 norm by alpha, and we add a constraint beta minus alpha equals 0. That's a way to get the problem in lasso form, or sorry, in ADMM form. And this is what the ADMM steps are. So let me write out where I got these from for you. And then for the next several examples, I probably won't write out the steps, but I'll just leave it as something you can check. So for the lasso, the augmented Lagrangian is this, y minus x beta squared plus lambda L1 norm of alpha plus rho over 2. This should be beta minus alpha plus W norm squared. And let's say the beta update. Okay, the beta update is to, let's say, take beta plus equals the minimum of all the beta terms, which is just this guy. So the least squares loss plus this guy, which is alpha minus W minus beta squared. Okay, and this is just a quadratic, so we can differentiate it and set it equal to 0, and then we get its minimizer. And see if I can guess that. So the only pieces that would be involving quadratic pieces are going to be beta transpose x beta, and this one's just going to be beta transpose rho times identity beta. So that's going to be my quadratic matrix Q. And then the things multiplying the linear term beta, okay, it should be y plus rho alpha minus W. It should be x transpose y. Okay, maybe I got that wrong, or maybe, okay, it looks like I got it right. So that's the beta update. Okay, the alpha update is going to involve the proximal operator of the L1 norm, because you can see that in my reparameterization, I guess here, I had an identity multiplying alpha. So from what I said in the last slide, we're going to get the proximal operator popping up. So it just looks like, in this case, let's say it as 1/2 beta plus W minus alpha squared plus lambda over rho L1 norm. So all I did is I took the pieces that involved alpha, which are these two pieces, and I divided it by rho to get something multiplying the L1 norm. And this is, we know this is just the proximal operator of the L1 norm, which is soft thresholding, with this parameter, lambda over rho, and with the argument being beta plus W. That's what I'm soft thresholding. So it's soft thresholding at the level lambda over rho of beta plus W. So, okay, what I did here is I just recall that this is the most recent value of beta we have to be using, right? Because I'm updating alpha after beta, and then the dual update is as always. W plus is just W plus beta plus minus alpha plus. Okay, so that's the 8mm algorithm. So let's inspect this guy. Even in the high dimensional case, I guess the first point to make is that this is always well defined, because this matrix is always invertible because of this piece. As long as rho is positive, this matrix becomes positive definite, even if x transpose x is singular. So it's always well defined. And from what we talked about, a couple lectures ago, look, we're going to be solving the same linear system at every step. Let's say we're going to be solving a linear system in the same matrix at every 8mm iteration. So we may as well compute a Cholesky of this guy, or QR. We could have done either. At the beginning, before we start the 8mm algorithm, and then that'll cost p cubed operations, and every time we apply it to solve a linear system, it'll just cost p squared. The alternative would be to solve this linear system kind of anew every iteration, and then that would be p cubed each time. And all those numbers would be improved if x was sparse. If x had some sparsity, and if I even had a structured sparsity pattern, it would be much better. Those would all improve. So that's a good idea. That's a common thing you see in, let's say, problems that involve like regression or logistic regression or anything with features, is that you get an 8mm algorithm which has linear systems in the same matrix, so you may as well factorize ahead of time. Okay, alpha involves soft thresholding, just because of the proximal connection, as we said. And this is an interesting phenomenon. I think it's actually kind of intuitive. What does this look like to you? Maybe for those of my statistician students in the class, what does that look like to you? Or the ML students? Or anybody? What does that look like? Yeah, exactly. That is ridge regression with tuning parameter rho. So let's get rid of the dual variables. That's just ridge regression. This is like soft thresholding the ridge regression coefficients. So it's kind of a neat connection, right? If you didn't know about the lasso and you knew about ridge regression and somebody said, give me sparsity, you probably would take ridge regression and you'd just do soft thresholding. And that's essentially how we're solving for the lasso. This is a rigorous way of doing it, but we're actually not quite doing ridge regression on y. We're offsetting x transpose y, so the score, if you think about it like as a likelihood, it's the score, it's the gradient, by like rho times alpha minus w, and then we're actually subtracting alpha minus w from beta when we're doing the soft thresholding. So it's very close to soft thresholding, yeah, of ridge.
Does it look like you're just doing like prox with adaptive step size? Because you can also run like proximal gradient, right? And then you do like very similar optimization. Let's say you're just dropping the primal update.
This is a good question. So, I think I have a slide on that. Yeah, I have a slide on varying rho. Varying rho it's not provably convergent. So it's something people do in practice, but we don't have theory that says that will work like as a strategy in general. This stuff assumes rho is fixed and arbitrary. For any value of rho, you'll get these guarantees. For particular values of rho, you'll get particular rates, but rho is always fixed. Varying rho is, I'll mention that in a few slides, it can be practically advantageous because it's seemingly so arbitrary, but there's not a guarantee for that converging. Other questions? Okay, so here's a comparison that I did of a bunch of algorithms that you've already seen for the lasso, plus some ADMM algorithms. And it's the same setup I've been showing you in the last lecture on coordinate descent, or whenever we had that. It's 100 random lasso problems. So the number of samples is 200, the number of features is 50. So they're kind of small. I'm just doing this kind of just give you an idea of how they converge. And I'm plotting the progress made on decreasing the criterion. This is actually the criterion gap. So it's the difference between f at iteration k and f at optimum, f star, for various algorithms, which each algorithm plotted in a different color. And with the dark lines being the average convergence over those 100 random problem instances. So here's coordinate descent. Okay, we already saw this performing a lot better than gradient descent. Gradient descent is, or proximal gradient, I should say, is kind of hiding here. It's like, it's in green here. It's being masked by accelerated proximal gradient, which is not a descent method, and giving us something here. And here's ADMM. Okay, so as an algorithm for the lasso alone, it's not looking great, right? Here's ADMM for rho equals 50, rho equals 100, rho equals 200. I think if I increase, in this example, if I increased it past 200, it would start basically matching proximal gradient, but much larger than that. If I take rho to be much larger, it starts getting worse again. So maybe it's going to be doing about as well as proximal gradient. And all of these algorithms, by the way, they have the same cost per iteration. It's just order n times p. They all have that cost per iteration. Okay. But I mean, it has this. You'll see that maybe like the saving grace of ADMM is twofold. One is that it applies very broadly, whereas coordinate descent applies to lasso-like problems, and proximal gradient to a bit more. But still, ADMM applies much more broadly. And we can, for example, we can do a parallel lasso with ADMM, which I'll mention shortly. We can actually parallelize things. So, what are some like general practicalities? A bit motivated by this, by that example. Well, I mean, this is what I said when I meant. This is also what I meant when I said it behaves like a first-order method, not just in terms of rates, but maybe it just kind of more broadly speaking, with any of these first-order method type algorithms, like ADMM or proximal gradient, which is a first-order method, you can usually get a relatively accurate solution in a small number of iterations. But converging to high accuracy is not easy. Requires a lot of iterations. So that's just, I think, roughly how you should think about ADMM. And if you're seeking a very high accurate solution, then you're wanting to use a second-order method. Or maybe you're wanting to run a first-order method until some point and then start using a second-order method from there. Choice of row in practice really changes how fast ADMM converges. And its role is actually very simple to explain. We can actually just go back to somehow, let's say this picture. If rho is very large, right, then we're actually placing a lot of emphasis on primal feasibility. Somehow the criterion is focusing a lot on driving AX towards B. Okay, and you can even see that somehow in the dual updates as well. If rho is too small, then we're not focusing enough on primal feasibility, and we're focusing more on minimizing F. And it may not be that easy for you to see this without somehow recalling the derivation for why this step size should be rho, but we can call that dual feasibility. Feasibility for the original dual problem. So you can think about somehow large rho as placing a large emphasis on primal feasibility, and small rho as placing a large emphasis on dual feasibility with respect to the original dual problem. And with that in mind, there's a kind of a trade-off as you vary rho, right? Because you would want both things to be true, of course, at optimum. So there's a nice practical kind of heuristic that Steve Boyd puts in this monograph, which has you look at the primal residual. So like observe what AX plus B, BZ minus C looks like for your current iterate. Take its norm, square norm. Compute something that measures the dual residual, which is how far you are away from stationarity, essentially, with your current iterate, stationarity for the original problem. And decide to either upweight or downweight rho depending on which one is larger. So if they're roughly equal, if these two are roughly equal, then maybe you keep rho as is because they have roughly equal emphasis. If the primal residual is getting really large in comparison to the dual residual, then you want to increase rho, like multiply by 2. And if it's getting really small and the dual residual is getting big, then you want to decrease rho. And so this is a strategy people use in practice, but it has no convergence guarantees. And I'm not aware of any strategies that vary rho that have good convergence guarantees. And this practicality I've said many times, which is like you can do it, you can bring up ADMM you can bring a problem to ADMM form in many different ways, and they give different algorithms, and I'll show you a nice example of that at the end. So that's an important one to be aware of. So I'm just going to keep giving you examples because I think they're kind of illustrative and they're interesting. So let's talk about the group lasso, which I don't think we talked about. I can't remember if we talked about this in the proximal gradient lecture or in homework, but if not, here's your introduction to the group lasso. It's like the lasso, essentially, but instead of asking for individual variables to be set to 0, we're actually now asking for groups of variables to be set to 0. So in a setting where there's a natural grouping for the features, and we'd like to select groups of features rather than individual features in some kind of regression setting. So to do that, we penalize according to the L2 norm of a block of coefficients in our regression model. So think about beta sub g as I vary g from 1 to capital G as being a block decomposition of beta. And this is just the L2 norm of a particular one of those blocks. This induces sparsity at the group level, just like lasso induces sparsity at the coordinate level. And if the groups were actually all of size 1, this would be the lasso. So that it would be the same as what you've seen. And you can replace this 2 norm by an infinity norm. Either one would, that would lead to similar behavior in terms of grouping. But the 2 norm seems to be more common for not really a good reason, I think. It's just a more common formulation that people look at. So we can put that in ADMM form, okay, by doing a similar transformation. I just replace the beta g in the penalty by an alpha g, and I introduce the constraint that beta minus alpha is 0, and I go through the updates I showed you. I go through the steps I showed you previously. The beta update is literally the same. Okay, the terms here, when I derive the augmented Lagrangian that involve beta, are the same. This changes. Okay, instead of soft thresholding, coordinate by coordinate, I get group soft thresholding. So this is my notation. R is the group soft thresholding operator. So it sends a whole group of variables to 0 or not, and I apply that at the group level. So that comes from the proximal operator of the L2 norm, which I believe you did derive in the homework. Right, we looked at the proximal operator of the L2 norm, and you saw it was a kind of like a group thresholding operator. And the dual update is the same. Okay. So I guess similar notes, somehow we do the Cholesky here. That would be advantageous in practice. This is what the group soft thresholding operator looks like. It sends x entirely to 0 or keeps x entirely away from 0. And x here would stand for like alpha g here. We do this to every block of variables. And this would kind of easily generalize if you had any other norm here than the 2 norm. You just use the proximal operator of that norm here. So this can be generalized quite a bit. Very interestingly, this is a case in which ADMM is just very flexible. If you have overlapping groups, so suppose actually this was not a partition of beta, so I didn't actually partition the groups, the coordinates into blocks, but I actually had overlapping groups. Like I decided for some reason to design my group lasso so that I have overlap in the groups. And there are several applications in which that makes sense, particularly applications that involve some kind of hierarchical structure of features that could make sense. So suppose this was one group, and this was another group, and that was another group, etc. Then it's actually quite hard to solve the group lasso problem. It's very hard to do proximal gradient, as an example. It's not hard to do ADMM. You just need to parameterize the problem properly. Okay, so this is an example in which the flexibility of ADMM really pays off. So this example is given in the Boyd monograph if you want to see the formulation that leads to the ADMM algorithm. Okay, and then moving away from regression, I have a couple more examples. Let's see. I have a couple more examples, and then I'll do consensus ADMM. So let's do these examples, and then we'll take a break. So moving away from regression, okay, I'm going to move into two problems which are both STPs. And if you didn't have ADMM and you didn't somehow try to specialize another algorithm, you'd have to apply an interior point method, and that would be really, really difficult. So without ADMM in this case, you're going to be calling, like Sadumi or Gurobi or CVX or something to solve this, and it's going to be like a very expensive STP to solve. So this is a sparse PCA. This is a formulation for sparse PCA that I thought maybe I actually wasn't here for this lecture, but when Siva covered for me early on, I hope he had talked about this problem. I was at least in the notes that I wrote. Why this is equivalent to sparse PCA. So maybe just like the very quick recap is that, okay, the PCA problem I can think of as find the projection matrix, find the matrix, let's call it P, that minimizes the reconstruction error between x and having projected x into a sorry, it should be on the right, having projected the samples, so the rows of x, into some lower dimensional subspace, subject to P being a projection matrix of rank k. So this is PCA, and the solution is take the eigendecomposition of x transpose x and take the first k eigenvectors and project into that eigenspace. That's what P will represent. That's how that is the solution to this problem. So it's just given by truncating the eigendecomposition after the kth eigenvector. Okay, but it's a non-convex problem because this constraint set is non-convex. The set of matrices that are projection matrices of rank k is not convex. This is equivalent to, okay, well, actually first it's equivalent to kind of by just expanding this, maximizing the inner product between X transpose X and P. So let's call this S, that's the sample covariance matrix in P, which another way of writing this, recalling what the inner product is that we associate with matrices, it's just the trace of the matrix S times P. So that's an equivalent way of writing that, okay, subject to the same constraints. And this one, so this is just expand the square. This one is actually quite a non-trivial equivalence. Sorry. I meant to write the trace form. This is defined as the convex hull of rank K projection matrices. And it's called the Fantope of order K. That's what its name is. And what happens is this non-convex problem is actually equivalent to its convex relaxation. If we take the convex hull of the constraint set, this is now a convex problem. Okay, these problems are actually equivalent. This relaxation in this case is tight. And this is due to a paper by Fan in 1949. I think it's 1949. Just why it's named the Fantope. So this is, I think, a very interesting result. It says that PCA is actually equivalent to a convex problem. It's this convex problem. And then these authors, both of whom used to be at CMU, and actually Jing, who's still he's my colleague, he's still at CMU. He's in statistics. They actually used his formulation in order to define a sparse version of PCA that was convex. So imagine that, so here I guess on the slides I called PY. Y stands for P in the notes. And I'm going to subtract off the L1 norm of the elements applied element-wise to Y to get sparsity in that representation of the projection matrix. So we get sparse PCA. So this is still convex because this is a concave criterion, right? Because the L1 norm is convex minus the L1 norm is concave. And that's a convex constraint. So, okay. It's a very, I think, interesting problem, and it has, of course, a lot of applications. How do we solve it? Well, we're going to rewrite this in 8mm form by swapping out. Okay, first thing we're going to do is we're going to move actually this constraint up into the criterion. So I'm going to write this as the indicator of Y being in the Fantope. I'm going to swap out Y in the L1 norm for a variable Z and add the constraint like Y equals Z. And okay, if I form the augmented Lagrangian, then what you're going to see is that the terms involving Y are quadratic plus linear plus an indicator of the Fantope. So if I collect that together, that's just a quadratic plus the indicator of the Fantope, which is projection onto the Fantope. So this is project Z minus W plus the covariance matrix over rho onto the Fantope. Projection with respect to the Frobenius norm here. And Z is just element-wise soft thresholding. So this is a very simple operation. This is just take this matrix Y plus W, soft thresholded element-wise, and this is my standard dual update. The only difficulty here is this projection, okay, which requires us to compute a partial SVD, or partial eigencomposition. So what you can check is that I can project onto the Fantope by taking an SVD of the input matrix that I'm projecting, and then clipping its eigenvalues. So I have to clip them at 0 or 1, essentially. Right? Because the Fantope is the convex hull of rank K projection matrices. My matrices in the Fantope have to all have eigenvalues between 0 and 1, and they have to have the trace equals K. So as long as you clip the eigenvalues appropriately while respecting the trace constraint, that's projection onto the Fantope. This is not a very difficult thing to prove. So still, this is actually, I think, a relatively simple algorithm, and it's much, much, much faster and simpler than like an interior point method. So it's a nice application of 8mm. Okay, and then this last one, I don't think I have time for this. Another example of an STP that would be very difficult to solve, like generically, but we have a nice ADMM algorithm for, is a matrix decomposition problem that's decomposing a given matrix called M into a sparse plus low rank matrix. Okay, so there are applications in which you might want to do that. This next slide gives you an application for like tracking in video surveillance. But how I can formulate that as a convex problem is that I have some matrix M. I'm going to write it as L plus S. L and S are my optimization variables, and I want the trace norm of L to be small, which remember is going to give me low rankedness. This is the convex relaxation of the rank, which is a non-convex operator. So this is saying I want L to be low rank. And this is saying I want S to be sparse. So I'm taking the L1 norm element-wise of S. And this lambda is just my tuning parameter for how much I'm somehow emphasizing low rank versus sparsity. And if you repeat the derivations similar to what we've done, you get a very efficient ADMM algorithm where this is soft thresholding as you know it, and this is matrix soft thresholding as we learned it in proximal gradient. So which again requires some kind of partial SVD. Okay, and I think this is a cool application if you want to read this paper to get a motivation of the problem. Manuel Candice and I think his postdocs and students apply this to video surveillance data, and I think it's just a neat application where let's say you have a bunch of video frames across let's say they're taken every second for like a long period of time. If you try to decompose that into something that's low rank plus sparse, okay, then the low rank stuff you get is, so now it's actually now a three-dimensional tensor, okay, because I have this across time, I'm stacking matrices. So this is actually low rank for that tensor because it's like two-dimensional things stacked in 3 dimensions. So I get the background being low rank, something that's kind of mostly constant across time. And the sparse stuff are the people that are passing through. Okay, this is like somehow, this is the transient stuff in the image and in the video, and this is the stuff that's more or less stationary. Okay, so let's take a break, and when we get back, I'll talk about consensus ADMM. Okay, guys, sorry about the quick break, but there is a bit more I wanted to cover before we wrap up today. So here's the plan. I'm going to tell you about the simpler form of consensus ADMM, and then I'm going to not tell you about the more general form, but it's in the notes. It's here, and I think once you understand the consensus ADMM in its most basic form and why it works, moving to a more general form is not difficult. It just requires like a little bit of modifications to the same step, but so morally it's like a very similar algorithm. And then we're going to have hopefully some time for me to talk about special decompositions at the end. So consensus ADMM operates on a problem of this form, which is very general, and maybe at first pass, if I didn't tell you about ADMM, this would seem like a problem that you could not really parallelize at all. Right? I have my criterion is the sum of fi of x. X is a shared variable across all of the functions. So this is very generic, right, as a problem form. And it turns out that by applying ADMM in a particular way, we can actually get a nice decomposable algorithm. And that's called consensus ADMM is the name of it. So we begin by reparameterizing the problem in this way. We introduce variables xi for each fi, so x1 through xb. We write this as fi of xi, and we write the constraint as xi equals x for all I. That's actually, this is a very important choice here. This is what defines consensus ADMM. This is not the only way we could have done it. And a very subtle difference, like saying xi equals xi plus 1, seems to be equivalent, would lead to a different algorithm. And actually, in this case, we're looking for a worse algorithm. So hopefully I'll see that after I go through the steps. So, okay, if we do this, the augmented Lagrangian looks like this. It's the sum of fi of xi plus Okay. How I should think about this thing, xi equals x. So how I should think about this constraint is like this. I should think about it as x1, x2, xb minus x equals 0. Okay, and I can think about this now as like some linear operator of my variable, which is x1 through xb x, that big thing, minus some other linear operator of my variable equals 0. So it's really a linear constraint on all my variables. And now the augmented Lagrangian just takes the norm, right, of this minus this plus the dual variable squared. But that norm I can easily split up component-wise, right? So the typical augmented Lagrangian looks like this, rho over 2, just to be perfectly clear, x1, x2, all the way through xb, minus x all the way through x, plus w1, w2, all the way through wb, writing a similar block decomposition for w, norm squared, right? Which I know this is a very simple point, but I want to emphasize it. That decomposes like this. Okay, so now when I go to do ADMM and I update, I minimize over the block x1 through xb, and I minimize over the x block. Okay, the minimum over x1 through xb, it decomposes by construction, right? Because if I want to minimize this over x1 through xb jointly, that's the equivalent to minimizing this over xi for each I, because it's just a sum. It's a sum of stuff that involves xi, and only the ith term involves xi. That's the whole point of this, of kind of casting the constraint like this. So the x update now, or the update for x1 through xb, decomposes in parallel into b updates, each one doing minimization over a smaller subset. And it's just exactly this, what I wrote down. It involves the prox operator of f. The update for x is actually quite simple. There is no other term that involves x than this in the augmented Lagrangian, or rather than this, depending on how you look at it. And if you minimize that, you just get an averaging operator. So this is sometimes called the consensus step in consensus ADMM. I'm bringing the variables into consensus by taking as my kind of consensus variable, my common variable x, the average of all of the xi's. And then I'm doing a dual update as usual. Dual update can also be done in parallel. Okay, that's consensus ADMM. And what you should do to convince yourself of this is that if you were to try taking the constraint as like this, x1 equals x2, x2 equals x3, etc., which is another way of introducing variables and then writing an equality constraint, you don't get a nice algorithm that decomposes. You'll have that the update for x1 involves x2, the update for x2 involves x3, etc. Okay, and so now you can see that somehow for more complicated problems, there are a lot of decisions as to how I kind of write these equality constraints, and there's some very interesting work that somehow now uses graph relationships to define these constraints in such a way that decomposes in some nice way. But the most simplest form is just define a common variable x, set everything equal to that x. That's called consensus ADMM. So it turns out you can actually rewrite these steps in an even more simple form, and this is special to this simple problem. So this is generic. Like if you had a more complicated problem, as I show you in 2 slides, it's the same. So that's all you really need to know in generality. If this was truly your problem and you didn't have somehow anything else going on than this, these actually simplify even further. And it's not hard to see that the average of the dual iterates is 0. And To see that, you use essentially this fact, which I told you about scaled form, that the scaled dual iterate is the running sum of residuals and induction. If you combine those two together, you'll prove that in this simple consensus ADMM problem, W bar is 0. And so with that, okay, this is truly the average of the x's. That's what this x is, because the average of the w's is 0. And so I can plug that into every iteration as the exact solution, and it just simplifies the form of the steps. Okay, it looks like this. Okay, so there's some intuition behind this. To minimize each fi of xi, in the step where we're defining the ith block of the variables, we're actually pulling xi towards the average. So we're pulling it towards consensus with all the other variables. And this variable wi is pushing us in the direction that tries to get us closer towards the average. Okay, so what we see from the dual update is that if xi is bigger than the average, then wi is increased. So the next iteration, we're pulling it even more strongly towards the average. If xi is smaller than the average, then wi is decreased. So we're trying hard to push it in the other direction towards the average. And now you can see maybe kind of simply, rho is your trade-off for consensus versus minimizing the function. If you take rho to be very large, you're going to drive variables into consensus very quickly. If you take it to be small, you don't place a lot of emphasis on that, and you're placing more emphasis on trying to get a small value of this criterion. Okay, so
Would it make sense to like ramp up rho at the end, so like you have low consensus as you drive your function down, and then you hold it together at the end so that it like solves the problem?
I can't really comment on whether I think that would be working well or poorly. I just honestly feel like that'd be hard to answer in general. I think it'd be an interesting thing to try, but some of my experience, like choosing rho is very finicky in almost any problem. So the strategies for varying rho actually tends to work well. So you look at the primal and dual residuals. So I would judge how far you are from consensus, and I would let rho move accordingly. But then in order to get guarantees, you want to stop varying rho at some point. So like maybe the combination of that with principled methods is like vary rho for 1,000 iterations and then don't vary it, because it'll converge after that. But hopefully by 1,000 iterations you've learned enough about the kind of particular function you're minimizing to settle on a good value of rho. Okay, so this is a more general form we can solve with consensus ADMM, but it's the same. Okay, it's the same algorithm just applied to a slightly more general criterion. So you can take a look at that if you'd like. So in the remaining 15 minutes, is that right? I want to talk about some special decompositions. Okay. So before we kind of talk about them in particular, I guess I want to draw a relationship between ADMM and block coordinate descent. So ADMM actually should remind you in some way of what you saw for coordinate descent, right? Because I'm minimizing something over one variable, another variable, another variable. In particular, in this consensus form, well, this actually looks like something like parallel coordinate descent. But it should remind you of coordinate descent, without consensus at least. And with that in mind, coordinate descent you should think about somehow pictorially as making the most progress when the blocks of coordinates are not very correlated with respect to the criterion function. Okay, if you have a very correlated criterion function, okay, doing something like coordinate descent is not going to be making very big progress, because moves along the coordinate axes are not really the beneficial moves here. The least correlated your problem is, or the less correlated problem is, the more somehow that like bigger moves can actually help you with coordinate descent along the coordinate axes. Okay, because the action now in minimizing your function is really aligned with directions that are kind of low correlation. So intuitively, how I think you should let this translate to ADMM is that there are maybe different choices for how you bring variables into bring a problem into ADMM form. you'd like to do so in such a way that the ADMM steps are actually addressing kind of orthogonal pieces of information in your problem as much as possible. Or they are making progress in the criterion in not very correlated directions. If you can do that, then often that leads to faster conversions for reasons that aren't theoretically somehow explained as well as they should be, but hopefully for reasons that make sense if you at least think about coordinate descent. So there are some examples. In fact, Adi is now here. He's a faculty here in statistics. He was a PhD student. He was my TA for 2 years for this course. We wrote a paper with this in it some years ago. And there's another paper by these are CMU folks. Actually, Matt was also a student of mine. I mean, a TA of mine in this class, Matt Wytalk. And then he's also was at CMU. So I guess this is all CMU stuff at this point. But there are some papers which kind of explore this and explain that for different, parameterizations, you can get faster conversions. So I want to give you a nice specific example, which is going to bring us all the way back to the first lecture, actually. In the first lecture, I gave you this example, and I said there are different algorithms you can apply, and one of them converges faster, and now you're going to see why, hopefully. At least you'll see why, in this case, ADMM converges fast compared to the other ones. So this is a problem in image denoising. So I'm given an image, and let's say y is a d by d image, and I want to fit an theta to y that has good error. So this is just the squared loss between yij and theta ij summed up across all I and j. And also it has low 2D total variation. So if I think about this as portraying the pixels on my image, so this is one index ij. I want my theta value here to be close to my theta value here, and also close to my theta value here, as measured by the sum of absolute differences. So I want the sum of this difference plus the sum of that difference to be small. That's a 2D measure of total variation. Okay, I can also write that in a more compact form if I string out y into a vector, and I call that little y. I do the same for theta, and I recognize that this is just a particular linear operator times theta. This is we call this the edge incidence operator of the 2D grid, but it's just the one that gives us these differences. That's all it is. So this is a more compact way of writing it. Okay, so if I gave you this problem, and you maybe looked to apply ADMM, then what you would do would be this. Okay, and this is maybe the standard way to do it, following what you've seen so far with the lasso and with everything else, which is introduce a variable z here in place of what I had as d times theta, because I know what the prox operator of the L1 norm is, so I want to arrive at that in my ADMM iteration. So replace that by z, write my constraint as theta equals d times z, and now I get this algorithm. Okay, this thing is the theta update involves solving a linear system in the matrix d transpose d rho plus I, but this is sparse in structure, so in fact this can be done very quickly. It's almost, if you look at the details for this, it's almost actually like it's almost like a 2D FFT, so this can be done very quickly. This thing is just soft thresholding, so it's also extremely fast. Okay, and this is the dual update. So every iteration here is roughly order n. Okay, it can be done very quickly. So it seems like a great algorithm, right? Because we have a very efficient way to do the 2D fuse lasso or 2D total variation algorithm. Okay, it turns out it doesn't converge that fast. It actually takes a while to get kind of high resolution or high accuracy solutions. Here's a second way to do ADMM that converges much, much faster. And hopefully you can at least morally see somehow why this is obeying this idea of trying to solve orthogonal bits of the problem. Let's duplicate. So here we've duplicated variables by just calling d theta z. I'm going to duplicate variables in a different way now. I'm going to go back to my 2D formulation. So go back to the first one with the matrices. And I'm going to, at every pixel, I'm going to either, I'm going to define a variable h and a variable v. Okay, so theta is going to be duplicated. I'm going to have a copy h of all my variables and a copy v of all my variables. And I've just gotten rid of theta from the notation for simplicity. So let's say h is equal to theta and v is a copy of that. And now I'm actually going to take the first term in the penalty, which is a horizontal difference. I'm going to plug in h there. I'm going to take the second term in the penalty, which is a vertical difference. I'm going to plug in v there. So v only ever appears in the vertical differences. H only ever appears in the horizontal differences. Okay, and so now they're somehow accessing different bits of the problem. What happens is that when I go to minimize over h and v, the problem actually splits up very nicely because the h minimizations only ever involve, do I have a picture? Differences in this direction. So it decomposes into actually a bunch of 1D total variation problems. There's no connection between the variables in this row and this one. There are only connections like this. And that I can solve rapidly. So actually, I remember this is a d by d grid. I have d 1D total variation problems of length d. Same with the vertical thing. I have d total variation problems in 1D of length d. Okay, and that I can do also very quickly. In fact, there's an exact way to do that. It's a convex problem, but in particular, it's a convex problem with a very nice structure. So you can use dynamic programming in this case. And you can do this in order d time, very, very fast. And so you just have essentially a bunch of those, right? And a bunch of those for the horizontal and vertical directions, and then the dual update. And that's the whole algorithm. So here's the difference in... All right, so I'm going to show you some empirical results. So here I have not a huge image, but not a small one. N is 60,000 here. That's the number of pixels in the image. And it's a 300 by 200 image. That's the dimension. So I guess it's not quite square, as I had in the slides, but it's just a notational change. And I used just an arbitrary color scale so you can visualize this. Let's suppose this was the data I was given, okay, and I wanted to denoise this. I wanted to get a piecewise kind of constant representation of this image. That is the 2 diffuse lossless solution. So I'm showing you what the solution looks like. And here's the difference in the 8AMM algorithms. Okay, they converge. So remember, I have the same cost per iteration, but they converge quite differently in this example. The even more dramatic thing is actually to look at what they do to the images themselves. So the criterion doesn't tell the full story. Here is 10 iterations in. 10 iterations in, I'm not sure if you can actually see because of the projector. You're missing a bit of the color scale here, but at least you can hopefully see and take a look at the notes if you want to see a better picture. 10 iterations in, this is very far from piecewise constant. Okay, there's lots of, there's like big dark blobs, and there's lots of kind of smoothness around the boundaries. This is already quite close to piecewise constant. And now I'm showing you 30 iterations. Somehow this is exactly piecewise constant. This looks exactly like the solution, and this is still quite far from piecewise constant. Okay, and 50 iterations in, this is still smooth around the boundaries, etc. Okay, so they behave quite differently in practice. And this is not an isolated example. This happens in image denoising kind of generically, I think, with these splitting algorithms. And it happens in a lot of other problems as well, with the moral being that if you can afford some creativity, try to set up the iterations so that they don't, so that they actually solve kind of decorrelated parts of the problem. Okay, that was actually all I wanted to say. So I guess we can end a few minutes early. I will see you guys on Monday.